Good morning. Hey, just before we get started, I want everyone to rise for the Pledge of Allegiance and the pledge to the Texas flag. All right? So, stand up. I'm kidding. All right. So today we're talking about exponential growth and decay. Exponential growth and decay is what is kind of the most realistic thing that you're going to encounter in math in your everyday life. Exponential growth, hopefully, is how your money spends its time in the bank. That's kind of the most realistic thing that you'll do. Exponential decay is mostly like half-life of chemicals, like radioactive half-life of chemicals, population decay over time. They have some great stories about introducing there's some great science stories based on introducing like deer onto an island that didn't have deer before, and it shows their population growth, and it's super exponential because there's no predators, and then their drastic decay after they realize that the island can't sustain all those animals. So pretty soon they're not out of food. So let's look at what we got going on here. Make sure whenever you're opening up your notes that you download the notes before you just try to view them online. There's a bunch of math applications on the Word document that I'm using, and you can't really see that in the preview. It just doesn't work in the preview like that. So with the Word documents, download the notes to whatever device you're looking at, and then view them. And the homework, though, is a PDF file, and that can be previewed, and that's fine. All right. Also, for starters, yesterday I rushed through number 11. I didn't read it all the way. It said domain, and I read it as range. So domain, number 11 is talking about domain. That should be A, not D, or whatever I put on there. So number 11 for yesterday's work, A. All right. Shout out goes to first period, Natalie, Bryce, and Jewel for pointing that out. So let's look at notes today. Exponential growth and decay. So for starters, the definition of the exponential growth and decay is it occurs when a quantity increases or decreases by the same rate r in each time period t. I'm going to repeat that. Exponential growth and decay, it occurs when a quantity increases or decreases by the same rate r in each time period t. Now, if you look at the equation that's highlighted below, it says y equals a times 1 plus or minus r to the power of t. Now, t is replaceable with x, okay? So t is time, and that's what we're talking about with exponential growth and decay. But in our calculator and in our functions and all that stuff, that will usually be where the x is. So here's what I mean by that. This is our exponential equation here. T and x are completely replaceable with each other. You can put in a t for time, or you can put in x for time, because x on the x-axis, we're usually talking about time. Now, this plus or minus here, this tells you if it's exponential growth plus or decay minus, okay? So if we think about it, if we're multiplying a value by something that's greater than 1 plus a rate, then it's going to grow. If we multiply a value by 1 minus a rate, something less than 1, then it's going to decay, okay? So the exponential growth function is y equals a times 1 plus r, close parentheses, to the power of t. And exponential decay will be y equals a times 1 minus r, close parentheses, to the power of t. Do you see how that works? Okay, so let's go through each of these real quick and talk about what each of them mean. All right, y, for starters, is going to be the final amount. That's what we're used to having. That's what everything equals. So this will be your final amount. This is your original amount or your initial amount, okay? Original or initial amount. The plus sign means growth. The minus sign means decay, okay? The 1 is there to control everything. So the plus sign means growth and the minus sign means decay. The rate is the rate of growth or decay, okay? So if I say a 3% growth rate, you wouldn't write 3. You'd have to change that to a decimal, All right, so your rate is usually going to be a decimal. In fact, it will always be a decimal. So we'll have 1 plus, if I said 3% growth, it would be 0.03. Don't forget, you have to move your decimal place twice whenever you're changing a percent to a decimal, right? And then t is time, or it's also x. So, but t is time. All right, so let's dive right in. I hope you understand what all of these pieces mean. Exponential growth and decay, we're just looking at how something grows over time exponentially, or how something decays over time exponentially. All right, so let's look at number 1 here. It says, tell whether the function shows exponential growth or decay as a percent. Excuse me. So, then give the rate, the growth rate as a percent. So first of all, how do we know if something is growth or decay? Well, we look at the number connected to the exponent, right? We're going to look at the number connected to the exponent, and we're going to see that that number is either greater than 1 or less than 1. We're talking about this number inside the parentheses. It's not always inside the parentheses because sometimes we won't have an a. Okay? So if this number in here is greater than 1, the number connected to the parentheses, or to the exponent, if the number connected to the exponent is greater than 1, then it will be exponential growth. If the number connected to the exponent is less than 1, it will be decay. So if you're looking at number 1 right now on your screen, it says y is equal to 250 times 1.25 to the power of 10. Well, is 1.25 bigger than 1 or smaller than 1? It's bigger than 1, so we're experiencing exponential growth. And what percentage of exponential growth? Remember, we added a 1, so we're taking away that 1, right? So our percentage of exponential growth would actually be 0.25 or 25%. Okay? Number B says 365 times 0.75 to the power of 6. Well, that number is decay, right? So we know that it's going, or it's less than 1, so we know it's going to be decay. How much less than 1? Also 0.25. So that will be 25%. So 1 minus 0.25 would give us that 0.75. So we're going to have 25% for that one as well. All right. C says 1.5 to the power of x. Well, notice that C doesn't have an a attached to it. Oh, it's 1, but it doesn't have an a attached to it. So this number is going to be that 1.5. So 1.5 is greater than 1. We're going to have growth. And how much greater than 1? 0.5. And we know that if we have 0.5, we have to move our decimal place 2 times to get the percent. 50%. I hope you can read that. 50%. So we know that that one will be 50%. The markers are all drying out. All right. And then D, the final one over here, is 2/25. 2/25. We know that that one is going to be decay because 2/25 is much smaller than 2/25 is much smaller than 1. So we look at that one. 2/25 is 0.08. So if I subtracted something to get 0.08, it would be 92% or 0.92. All right. Okay, so here's what we have here. Number 1A was growth because it was 1.25. So that gives us a 25% growth. 2 was 0.75. That gives us a 25% decay. 3 was 1.5, which gives us a 50% growth. Now notice all I'm doing is either adding or subtracting 1 here. Okay? And then D was 2/25, and see my marker's drying out. It's decay, and it gives us a 92% decay. And once again, here's how that works out. Because all my markers are drying out, I'm going to use paper here. So we know that's decay we know that the thing is going to, can you see that? 1 minus r equals 2/25. Well, 1 minus r equals 2/25. We're going to solve for r, so we're going to subtract 1 on both sides and then multiply the whole thing by a negative. So we're going to end up with negative r equals negative 23/25. Then we're going to multiply the whole thing by a negative 1 and get r is equal to 23/25, which if you type that in your calculator, you will get r is equal to 0.92, which means we move our decimal place over twice and get 92%. Okay. All right. Number 4, 5, and 6. Let's see here. Yeah, try pausing the video real quick and see if you can figure this out on your own. And I'll go over each of them in just 1 minute. Okay. All right. Number 2 is talking about ticket sales for a movie. And if you look at the data, it says day 1 is 1,600, day 2 is 1,280, and day 3 is 1,024. It says, does the data represent exponential growth or decay? Well, is it increasing or is it decreasing? If something is growing, it's increasing over time. If something is decaying, it's decreasing over time. Okay? So we know this one is going from 1,600 to 1,200 to 1,000. So I know that's decay. So our answer for A would be decay. And then B, if you look at all those functions, only one of them represents decay. You remember inside those parentheses, we're looking for a number less than 1. So we know that 0.8 is less than 1. That's going to be the only one that shows decay, so it's got to be C. If you want to type that in your calculator into y equals and check a table, the table should look very similar to what you have over here with the data listed. So 2 is decay, and then equation C. 3 says the function blah models the amount of money in a certificate of deposit. So that's called a CD. You can get one today if you would like, kids. You just got to go through your parents. You put your money in a CD, and the bank tells you what you're going to have after a set amount of time. So it says, how much money will there be there after 6 years? Excuse me. How much money will there be there after 6 years? So we have our equation 500 times 1.035 to the power of 6. Okay? And it gives us $614.62. You cannot raise it to 63 cents because you must round down for banks. Banks are not in the business of giving money away. So you can't round up and have them give you an extra penny. They round down and they keep that penny. There's a little life lesson for you. Whenever it's in your favor, it doesn't happen. So if it's in the bank's favor or in the seller's favor, so anytime you go to the store, you buy something for $7.99 plus tax, that tax is always rounded up in the store's favor and not in your favor. All right. Number 4 says the function blah, where x is time in years and models the population of a city. What will the population be in 7 years? Well, if you look at the equation for number 4, we see that 0.98 is less than 1. That shows that it's decaying, so it should be less than 200,000. We look and we see that it's 1,000 or 173,625 point something at the end of 7 years. Well, it's humans, so you have to round down to the nearest whole number. Round down to the nearest whole number. You don't want one arm walking through whatever event you're doing because you had 0.1% of a person. Okay, we don't take that portion of a person and throw them into in the mix. We always round down to the nearest whole number, so it's going to be 173,625. Number 5, it's asking when. So it says in 2000, that's a very important number. In 2000, that's year 0 on your table data. Year 0, when it all starts, when you first gather your information, is year 0. After you run it through 1 year, that becomes when X is 1. Okay, that's year 1. The population of Texas was about 21 million in year 2000, right? It is growing at about 2%, so it's going up. At this growth rate, the function f of x is equal to 21. Notice they're speaking in terms of millions. It doesn't say 21 million. It says 21 times 1.02 to the power of x gives a population in millions x years after 2000. Using this model, in about what year will the population reach 30 million? This is a great calculator question. You can break out your calculator. You can type that into y equals, and then you can just hit second table, and it'll show you. Now we're looking, all these numbers right here are in terms of millions. See how it's 29 point blah, 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 28 point blah, blah, blah. That's actually 28 million something 100,000, right? So we see in year 19 that it finally goes over 30 million people. Year 18 is not 30 million. It says, when does it reach 30 million? It doesn't do it in year 18. It does do it in year 19. So we know that that's 19 years after year 0, which would be 2019. In the future, I mean the past. The past. All right. Number 8. Or sorry, page 8. Number 6. The population of a town decreases. So you're having to set up an equation here at a rate of 3%. In 2000, there were 1,700 people. Write an exponential function to model this situation. Then find the population in 2012. So 12 years after year 0, right? Your equation will look something like this. Y is equal to 1,700. That's our original population. And it's exponential decay. So we're using a minus sign. We're changing 3% to 0.03. We had to move the decimal over twice. And then we're changing t to 12 because year 0 is 2000. Year 12 is 2012. All right. And we got 1,179.53, but we know we can't include that 0.53 of a person, just a pair of legs walking through a room or something like that. We're not including that. So we bump it down to 1,179. All right. Number 7. By the way, if you need a pause or anything like this, feel free to do so. I only have 2 more questions here. Number 7, the value of a truck bought new for $28,000 decreases 9.5% every year. That's another important lesson. When you buy a new car, right when you drive it off the lot, it is now a used car and it starts decreasing in value. Okay? So don't ask mom and dad for a brand new blah, blah, blah whenever you turn 16. You're going to wreck it anyway. So, the value of a truck bought new for $28,000 decreases 9.5% each year. Write an exponential function to model this situation, then predict when the value will fall to $5,000. This is another great calculator problem. First, you got to create the equation, which is 28,000 times 1. It's decreasing, so minus 0.095. We took 9.5% and moved the decimal place twice to get 0.095 to the power of t, or x, on our calculator. Okay, we type that in, and go ahead and do that. Pause. Okay, I hope you paused. Type that in and look at your table, thumb through it until you see the price will fall to $5,000. And let's see here. I'm going to pause too. All right, when we type that in our calculator, we see that we get this. And when we thumb down through, we see that after quite a few years, the price finally drops past $5,000. Now, notice that in year 17, it says $5,130.80. That's not $5,000. So you have to say in year 18, even though it says 4,643, we know that it will fall to 5,000 in that 18th cycle. Okay. So it will be 5,000 in year 18 to, well, let's see, year 18. Okay. The original value of a painting is $9,000. We're on question number 8. $9,000 and the value increases by 17% each year. Write an exponential function to model this situation. Then find the painting's value in 15 years. Well, we know that it's increasing in price, so we know that's exponential growth. And we know it's growing by 7%, so it's 0.07. So our equation looks something like this. Y equals 9,000 times 1 plus 0.07 to the power of t. So We type that in our calculator and exchange t for 15 because it says how much will it be after 15 years. And we're going to get $24,831.28. By the way, for all of you who are talking money in class, like I want to be rich when I grow up or whatever, money takes time, okay? So save your money, invest it wisely, leave it alone, and give it time. Time creates money, all right? You have a wonderful day. Have fun on the practice problems, and if you have any questions, feel free to type them in the comments section. We're going to have Google Classroom questions, so I still have a handful of people in every class period who aren't doing their Google Classroom questions. So those are going to be Monday through Thursday, every single day. And I also got word that y'all are going to get Fridays off. So every day we have school, right? Monday through Thursday, we're going to have a Google Classroom question. On Thursdays, it's going to be a little bit more extensive, all right? So make sure you're doing your practice problems and make sure you're doing your Google Classroom questions. I will see you maybe later.